Now let's examine extending a bipolar current mirror to using the bias generator, the V bias generator, to bias multiple current sources as we did with the MOS just a moment ago. So here we have our V bias generator. We're going to take a diode connected bipolar transistor. And here's our reference current, IR, through our reference resistor, RR. And of course the reference current flows partially into the collector, IC1, but we also get some base current that flows, IB1 here, and we're going to connect this reference generator up to a number of other current sources. This current source goes to bias some circuit, the current I0. We're going to have another current source that's also biased from that same bias generator. And we'll assume that we have N number of current sources, all outputting a current I0. So this would be Q1, Q2, Q3, all the way up to Qn. Now each of these transistors draws base current. So here we'd have IB2, here we'd have IB3, and here we'd have IBN. So if we were to do KCL at this supernode here, so all these transistors are connected, so we have a supernode. We would see that IREF is equal to IC1 plus IB1 plus IB2 plus all the way up to IBN. And if we assume that all transistors are equal, then we can assume that IC1 is equal to our I out, ideally. And we would say that IREF is equal to I out plus I out times N divided by beta. These are all of our base current terms. And we can factor this out and solve for I out. And we can find I out is equal to IREF divided by 1 plus N divided by beta. So this is problematic if you remember this denominator here is what we call a systematic error. In other words, we'd like our output current to equal our reference current, but because of the finite beta of the transistors, it doesn't. And of course, this is worse than the prior expression that we looked at for a bipolar transistor, because as we increase the number of transistors that we're biasing, we get this increase in the size of the denominator, and of course our error increases. So one thing to ask ourselves is, how do we reduce this error? And the way we do it is with what we call a buffered bias generator. Alright, so what we're going to do is we're going to take our current source, or sorry, our voltage reference, and we're going to add a transistor in the loop that would normally be comprised of the diode connected transistor. So here we have the same RREF, we have an IREF, this voltage would be our VB, and we'll call this transistor Q1 and this transistor Q2. So normally going in this direction, we would have all of our base currents for whatever transistors we connected to the device, IB2 plus IB3 plus all the way up to IBN. Of course, coming back into this device, we have IB1. And we'll call the base current flowing in here IB1. Sorry, let's label this transistor Q1A, and we'll call this IB1A. Alright. Now if we do KCL at this node, we see IREF is equal to IC1 plus IB1A. And we can see that IB1A is going to equal IB1 plus IB2 plus all the way up to IBN divided by beta plus 1, because all of these IB1, IB2, IB3 currents are coming through the emitter. So we're just going to take that emitter current by summing all of these base currents and divide it by beta plus 1 to convert it back to IB1A. Converting this into terms of collector current, we could say IB1A is equal to N times IC1 divided by beta times 1 divided by beta plus 1. Now we can substitute back into our original reference current expression. Say IREF is equal to IC1 plus N times IC1 divided by beta times beta plus 1. And of course, we want to write this in terms of output current, so we note IC1, we desire IC1 to equal the output current for all of our other devices. So we could say that IOUT is equal to IREF divided by 1 plus N divided by beta times beta plus 1. So this is a much better situation than we had before, because we're effectively increasing the beta of our transistor. So this is called a beta helper. We're effectively squaring our beta. So anytime we add this device into our current mirror, into our bipolar current mirror, we call this a beta helper current mirror. And effectively what this Q1A device is doing is buffering the it's adding some buffering to the circuit. So this is an emitter follower, and remember, an emitter follower can't provide voltage gain. It's just a voltage buffer, a unity gain amplifier, but it can add current gain. And so that's what it's doing, is it's buffering the current. So it reduces the current demand from the reference. Okay, so with that we'll continue on with some more current mirrors specifically designed to increase the impedance in a bit. One thing I wanted to say here is that we can also figure out what the reference voltage is at this node, and it's different than for the standard current mirror because we have to go, if we just do a KVL loop up to this node through well-defined voltages, we have a VBE here and we have a VBE here. So we go plus 1 VBE, plus 1 VBE, or the voltage at the other side of the reference resistor is 2 VBE. So we would have to size our reference resistor just a little bit differently in order to get the desired current, because the VBE drop effectively is larger for this transistor. And with that, we will look at some more interesting current mirrors in the next